So in this video, I'm going to give you an example of how we might apply boundary conditions to a real problem. All right. And so the problem that we're going to consider is the following. We're going to have a boundary right here. On one side, we're going to call this material 2, and that's going to be silicon. On this side will be material 1. And we're going to say that's free space. Free space has a relative permittivity of 1. Air is very close to a free space. It's like a very small fraction higher permittivity. For some application, that really matters, but for now, let's just think of this as air if you prefer. For silicon, it turns out it has a relative permittivity of 11.67. All right, now the problem that we're going to start out with is that we know the electric field on one side, and we're going to say that it's 1,000 volts per meter, and we're going to say it's pointed in the x direction. And we're going to define our coordinate system like this, right, where this is the x direction. And so this is 1,000 volts per meter pointed in the x direction. And the question is, what is the electric field on the other side, right? So this is all silicon right here. All right, what is the electric field at its side? All right, so let's apply our boundary conditions. And our boundary conditions are that we take the n hat vector and dot it with d1 minus d2 equal 0. All right, so let's define what this is. First, n hat is going to be a vector that points into material 1 and is perpendicular to the boundary. All right, so n hat is going to be this direction. All right, so n hat is going to be negative x hat because it's in the opposite direction from x hat. D1 is going to be epsilon times E1, which is equal to 1,000 times epsilon naught times x hat. All right, so that's D1. D2 we don't know, but we can say that D2 equals epsilon 2 times E2. All right, so let's put all this together. So n hat, we're going to substitute and put in a negative x hat right here. So this is negative x hat dotted with D1, which is 1,000 epsilon naught x hat minus D2 equals, I'm going to write down 0. Really, by the way, just so it's clear, really this boundary condition is rho s. It's charge built up at the surface. But in this case, we have two dielectrics. Both silicon and free space are both dielectrics, and so we know this equals 0. So we can just set this equal to 0 and get rid of the charge. All right, so let's now distribute this out. And we've got minus x hat dotted with 1,000 epsilon naught x hat minus x hat dotted with D2 equals 0. All right. Now here we've got minus x hat dotted with 1,000 epsilon naught x hat. And so the x hat dot the x hat becomes 1. And so it becomes minus 1,000 epsilon naught. All right. We're going to take this, the two minus signs are going to cancel. And so this is going to become a plus d2x, which is to say it's the x component of d2, because that's what the dot product does. It only picks out the x component of d, and this equal to 0. Let's replace that with epsilon 2 times e to x. And from here we can get that e 2x equals 1,000 times epsilon naught over epsilon 2. Epsilon 2 we can then rewrite as being epsilon R2 times a free space value, and that crosses out. And so this becomes 1,000 over 11.67. And since E2x, this is the x component specifically, we can now say that E2 equals 1,000 over 11.67 in the x direction. And there we have our answer, right? So granted, you could have applied this qualitatively and just say, well, hey, I know that the electric field is going to scale by epsilon from one side to the other. But oftentimes, if it's not quite that simple, if you have coordinate systems that aren't aligned, it's easier just to directly apply this main boundary condition that n hat dotted with d1 minus d2 equals rho s, and just substitute what you know and just solve for what you don't know. And that's a boundary condition. There's another example in the notes that I'm not going to talk about, but I'll at least set it up for you, and you can take a look at the details. And that problem is you have a conducting sphere, right? A perfect electrically conducting sphere, and you embed that inside of an electric field. And the question is, where do you get charges built up on this sphere, and how do they get distributed? That example is in the notes, and I'll stop there. And we'll move on next. The next lecture, Fields and Waves number 10, we're going to conclude electrostatics by finally filling in the last missing link between these three big quantities: field, charge, and potential.